I will calculate the transient response of current and voltage in the presented system using classical method. In DC circuits, a change in voltage only causes a step change in current only in purely resistive applications. If there is a coil or a capacitor in the circuit, the change in the voltage and current are no longer instant. Transient response of the circuit can obviously be represented by mathematical function, which I will calculate for the represented circuit. Values for elements are resistor 1 equal to resistor 2 equal to 40 ohms. An ideal current source with a value of 2 amperes and 100 mH coil. Analysis should start by calculation of the current flows for the state before and after closing the switch. First, let's calculate it for a closed switch. We know that for a direct current circuit, the coil is the short circuit, meaning zero resistance, and the capacitor is a break in the circuit, meaning infinite resistance. Current is lazy and will flow along the smallest resistance line, this way. It goes only here, avoiding the more difficult trails with resistors on the way, simply because there is a short circuit here. We can take into account that current 1 and current 2 are equal to 0, and coil current is equal to the entire current produced in the current source, which means 2 amperes. Now let's analyze the state after opening the switch, which is equally simple and does not require calculations but only deduction. From Ohm's law, voltage is equal to current multiplied by resistance. In this case, 40 ohms multiplied by 2 amperes, which gives 80 volts on resistor 1. The current 1 will be equal to the value of the source, because the source is connected only with resistor 1. That's why current 1 is equal to 2 amperes. The right side is cut off from the source after opening the switch, therefore current is equal to 0 after disconnecting it from the source. Of course, the coil will store some energy before opening the switch that between 2 amperes and 0 amperes will create transient state with a time constant. The current flowing through coil and resistor 2 is the same thing in the circuit on the right side. We can proceed to write a few simple assumptions. The first of Ohm's law is that voltage is equal to multiplication of current and resistance. Writing it to the right side of the circuit, current of the coil times the circuit resistance, which is equal to resistor 2, gives voltage. Current and voltage have in their designations T in the brackets because they are in a function of time. After dilating them, we can see simple Ohm's law. Current of the coil consists of the constant part and the transient part, meaning there is a transient shape and the fixed constant value in the current and voltage equation. Fixed constant value of the equation in the circuit after the transient state, in this case, is equal to 0, as we stated before. We put 0 in the constant part of equation and then write the equation for the voltage prevailing on the coil, which is the multiplication of the induction of the coil and the derivative of the current on the coil. As we stated before, current on the coil can be described as simple Ohm's law. I put this term into our new equation with a derivative, obtaining a new equation. Known values for induction of the coil and resistance can be substituted into the formula. In the next step, our current of the coil is written in a different form. I have used the concept of time constant and Euler number. This number is on each scientific calculator, which will simplify calculations. According to the shown formula for the derivative, in this case for e to the power of any number, after calculation gives the same value only by erasing the derivative. As we can see in the obtained equation, the designations can be shortened because they are multiplied by all elements. After shortening equation, we get this formula. We move tau to the other side and divide minus 40 by 0.1. After doing it, we get a tau equal to minus 400. You should know that the time constant for RL circuit is equal to inductance divided by resistance. In this case, 0.1 divided by 40, which gives 2.5 milliseconds. The transient part of the equation can be written in the form of time divided by time constant, power of current. Transforming this equation, we get tau equal to minus 400, exact same value as obtained before. As we know, division, in this case time divided by inductance divided by resistance, can be converted into a multiplication by turning the numerator with denominator, giving minus time divided by 1 multiplied by resistance divided by inductance. Knowing this data, we can write the final equation for current of the coil, containing transient and steady state. Current of the coil is equal to 2 amperes, after closing and 0 amperes before closing. Tau is equal to minus 400. The voltage across the resistors results from the Ohm law and is only multiplication of obtained current and resistance too. The waveforms were drawn in Excel and confirmed by a free circuit simulator LTSpice. Simulation is important because it confirms the correctness of the results obtained. The duration of the whole transient is estimated to be 3 to 5 times the time constant. By comparing the duration of the achievement of about 63% in the simulation and the calculated result, we can conclude that the calculations are correct. 63% of the value corresponds to one time constant. It can be estimated graphically from LTSpice according to this drawing. As discussed before, the time constant for RL circuit is induction divided by resistance, or 0.1 divided by 40, which in this case gives 2.5 milliseconds as stated before. In 2.5 milliseconds in LTSpice we can see the value of 0.72 amperes. It corresponds to the value of 2 amperes divided by Euler number 2.72, which is true to the theorem of one time constant explained before. It confirms correctness of our all calculations.